Let's start today's class. So in the previous class, we learned about the structure of hard disk drive, and then also we briefly covered the structure of architecture of SSD, the solid state drives. So why do we need to understand the architecture or structure of these storage devices? So it is because if we understand the architecture of those storage devices or storage systems, then we can work for improving the performance of storage systems, or also we can work for some various aspects of the storage device, such as cost, reliability, and some other issues. So it is because, so I believe everyone knows that the computer systems are composed of many layers of abstractions. So with abstractions, we can understand only required things. That means actually the computer systems or actually the real systems like car or some other machines, or also the computer systems are very complex, and then it's not easy to understand the detailed behavior or detailed architecture of this inside of architecture of these systems. It's very complicated. But if we only understand the interfaces between adjacent layers, then, and also if we understand some interface signals or interface protocols between layers, then we can work for a certain layer. So for example, this is the computer system architecture, and upon this computer system architecture, there is operating system layer. Here, operating system layer is the software, and then computer system architecture is a mix of software plus hardware. Okay, and then also you can have the additional layer on the computer system architecture, like the real processor architecture. It's a hardware. So actually, there are many abstractions between these layers. Also we rely on many abstractions on these software layers, because hardware is a little bit complex. As I believe the hardware is more complex than the architecture of software. Also the software is composed of many layers, so software is also complex, but so the hardware is also complex. So in order to minimize these complex systems, then we use the technique of abstractions. So like operating system, for example, in the operating system, think that our computer system has infinite resources of processors, also infinite resource, not infinite, but nearly infinite. So actually the large amount, the amount of resources is very large. So the large amount of memory. So when we write software code, we do not consider about this size of the memory spaces. Also, we need to consider sometimes, but we do not consider the resources in processors. Okay, because with the operating system, so operating system provides the processor. So it's an abstraction of a CPU. Also, operating system provides virtual memory. So with the virtual memory, we think that this computer system has very large amount of memory, so large memory spaces. But in reality, in the computer hardware, we already know that the size of the main memory is limited. Also, this actually we know that the main memory is very expensive. So we with the virtual memory system, we use the part of the main memory as cache, and then also we use the part of the storage space as the swap space, because it's fast and expensive, but and the hard storage devices is cheap and very slow. But in the software view, so in the aspect of the software, because of this virtual memory, then software think that, oh, this computer system has very large memory. And then it's also same to the storage system. So in the memory hierarchy, we think that storage is some low-level memory. Also, the storage system is called the secondary memory. Okay, so that means that this is the operating system, and then operating system handles the storage system, so or storage devices. But operating system just handles the storage device as block devices. So that means in the storage system, there are many blocks of memory spaces, and then we think that our user data, also our data, can be stored in this block memories persistently. So like persistently, so that means that the data is not erased, data is not removed, even though the power loss or the system crashes happen. Okay. So block device means that we just access data in the storage system with the very simple commands such as read, write, erase for a certain block. So operating system just generate these commands such as read, write, erase blocks. That's it. So the storage system receives these command, but inside of this storage system is very complex. Also, there are many kinds of storage devices such as hard disk drives or solid state drives. And then so this is the modern storage system actually. So in the old age of the computer system has some tape drives or some very slow storage systems such as floppy disks or some zip drives or tape drives. So these are very slow storage systems. But operating system just handles the storage system as the block devices. So it generates a very simple commands, and then it just look at these commands simply: read, write, erase, block. That's it. But inside of this storage system is very complex. So for example, hard disk drive, as we learned in the previous class, the hard disk drive is the mechanical drive. So data is stored in the surface of platters, and then we learned that the platter rotates, and then the arm moves around the track on the platters, and then in order to access a certain sector that is similar to the block of the operating system, but the size of the sector can be different from the size of this block. So this arm moves around the tracks and then approach to the target sector and then read the data from this platter, so hard disk drive, and then it takes time. It is because of some mechanical feature of hard disk drive. So when we design the operating system, the operating system just see the storage device as some memory, block memories. So we do not consider the structure of this storage system. then the performance can be very low compared to the some designed performance of the storage system. Because, for example, in the hard disk drive, based on the location of the target sectors, the performance of the hard disk drive can vary. Okay. That's why we need to understand the inner architecture of storage systems. So in the view of the operating system, the storage system is very simple, but in reality, the storage system is very complex. That's why we need to understand the architecture of the hard disk drive. And then let's consider the solid state drives. So I already explained the unique features of flash memory. So flash memory is a kind of non-volatile memory. And then this is not a mechanical drive because the flash memory is a kind of solid state memory. So like the RAM. So actually this flash memory is developed from the very popular read-only memory like EEPROM. So we widely use this EEPROM as some storage space for CMOS BIOS on the computer mainboard. Okay. And then the main feature of this EEPROM is that the data is not erased even the power is lost. But the performance is low. It's lower than the performance of the RAM. Because so just to remember that the performance access latency of this flash memory is asymmetric. So that means the read latency is relatively low, but it's about 1,000 times slower than the speed of the DRAM, but it's relatively fast compared to write or erase. And then write is about 10 times slower than the read speed. And then erase is very, very slow because of the high energy for this erase process. Also, the access granularity is asymmetric for read, write, and erase. So these are the main feature of the flash memory. And then as SSD use the flash memory as the main storage media, the SSD needs to handle these features. So that means like other storage systems like hard disk drive and these other storage systems, operating system just gives very simple command, read, write, erase blocks. And then SSD need to receive this command and then responds to the command from operating system. But based on the management scheme inside of SSD, the performance of SSD can vary, okay, like hard disk drive. So we can easily understand that the performance of a hard disk drive is determined by the location, the scheduling, like the location of the target data. So that means so this is the data queue, and then the request is stored in this data queue, and then based on the scheduling, the performance of the hard disk drive can vary. It's the same to the SSD because of this asymmetric performance for read, write, erase, and then also the access granularity of read, write, erase processes. The performance of SSD can vary by the management schemes. Okay, that's why the SSD. So we can work for the performance of SSD based on these features. Also, we can. That's why the SSD requires somewhat complex firmware, that is a system software, to manage flash memories. Okay. Okay. So So in the previous class, we learned the SSD is composed of the software part and the hardware part. Then it's the same to the other I/O devices. And then software part, the SSD has a storage processor, so like an embedded processor. So we usually use ARM processors for SSD processors. And then SSD may have DRAM because SSD processors, the SSD processor needs to run system software called firmware, and then also SSD processors manage the data transfers between NAND flash packages and storage interfaces such as SATA or PCIe. Also, in order to manage the NAND flash packages, SSD requires some address translation. So we will learn about the address translation of the solid state drive in the today's class. So this DRAM space is used for some firmware or some address translation or data buffer for data transfers. Also hardware part, this is the NAND flash packages. And then data is stored in this NAND flash chips. Okay. And then if you know about the behavior of the DRAM, so we based on the DRAM scheduling algorithm, the performance of DRAM can vary. It is because the DRAM has some hierarchies such as rank, bank, and then also many chips. But the chips, the data is shared, data bus is interleaved between many chips in the DRAM system. So actually, in the DRAM DIMMs, we need to consider the bank or rank or row or column of the memory space in the DRAM. And then based on this hierarchy, the performance of a DRAM package may vary. So that's why the algorithm of the DRAM controller is critical for the performance of DRAM systems. So we need to consider the this location of the requested data, this bank, rank, column, or row inside of DRAM. And then it's the same to the NAND flash packages, because like DRAM, this is solid state drive, and like DRAM, the NAND flash packages has also some hierarchies. So we will learn about the hierarchy like this. So it's a channel, way, and die, and plane. Okay. So these are hierarchy inside of the NAND flash chips. So channel is very similar to the DRAM channel. So actually a single memory controller is assigned to each channel. And then way is the number of different chips connected to this NAND flash bus. So multiple flash packages can attach to this NAND flash bus, and then the bus can be shared by multiple packages. Also die. So this die is very similar to bank of the DRAM system. So that means the die can work independently inside of a package. And then also these dies share the interfaces between the NAND flash bus and the inside data bus. And then plane. So multiple plane work simultaneously. So actually when we consider the DRAM, so the multiple chips work simultaneously. That means each chip is assigned to the 8-bit data of the DRAM bus. And then by accumulating the multiple chips, usually we use the 8 chips of the DRAM DIMM. So we can generate the 64-bit data bus from DRAM from a DRAM DIMM. And then this concept is very similar to plane. So there can be multiple plane, and then each plane works simultaneously. And then so same commands are provided to the plane, multiple planes, and then each plane work handles the same commands to the flash memory. Okay. So in the NAND flash package, there are some hierarchies such as channel, way, die, and plane. And then based on the data location, and then based on the some scheduling, the performance of NAND flash package can also vary. It's similar to the DRAM systems. Okay. Okay, let's talk about the parallelism in NAND flash memory. So also this parallelism is also exist in DRAM systems. So we frequently call the DRAM system parallelism in DRAM system as memory level parallelism. It's called MLP. So the similar concept can be applied to the flash memories, because flash memory also has hierarchy like DRAM. Okay, so we can call this parallelism as a flash level parallelism. Okay, the first parallelism we can use is channel striping. So, and it's very simple actually. There are multiple channels in the NAND flash memory. So that means the SSD this is the SSD system, actually the SSD processor. And then there are multiple memory, it's flash memory controllers. Okay. So it's a flash memory controllers. And then each controller handles each channel of flash memory. So that means each memory controller, the multiple memory controllers can work in parallel. So that means the request to the flash memory can be assigned to the multiple flash memory controllers. And then if these requests can be serviced in parallel. And it's obvious actually. So if this is CPU, and then if there are multiple channels for DIMMs, right? So that means that a CPU has multiple memory controllers. So then we already know that memory controllers can work in parallel. So if we use the multiple channels, then we can also increase the data bandwidth between CPU and DRAMs. Also, we can increase the performance of the system. And it's the same to the flash memory. If there are multiple channels in the SSD, then multiple requests can be handled in parallel. And then that's obvious. So if the multiple requests can be handled in parallel, then we can increase the performance of this SSD, right? So, for example, let us assume that there are two requests, A and B. And if A and B, these two requests are assigned to the same channel, then we need to serialize these requests, and then the performance of that SSD will be low, okay, because the commands are serialized. But if the request to flash memory is assigned to the different channels, then we can increase the performance. Okay. Then why we need to learn this? Why do we need to learn this? Is it the work of the operating system? So actually in the DRAM, so we already know that. So I believe everyone knows. Operating system converts the virtual memory space to physical memory space. That means the virtual address to physical address. So actually, the main memory is accessed by these physical addresses. So based on these physical addresses, and then based on some mapping rule of the DRAM systems, the location of the data is determined. It's the same to the SSD. It's the same. So I said the storage device is the block devices. So operating system generate request based on the block address. So for example, usually we call this block address as LBA. That means the logical block address. Okay. And then if the logical block address is determined, and then this block address is converted into some physical location of the storage systems. For example, in the hard disk drive, logical block address is translated in the location of the data, target sector, that means the target sector. And then we already learned that the location of the target sector is composed of flat number, surface number, and then track, and then sector number inside of the track. But usually in the hard disk drive, so we don't know how this location is composed based on the logical block address. That is not revealed to the operating system. But usually the smaller logical block address is located near this cylinder, and then the larger logical block address is located to the outer track, so inner track or outer track. But it's unknown, so it's not revealed to the operating system. It's unknown. But we can think that the location of the logical block is assigned to the hard disk drive sequentially from inner space to the outer track, inner track to the outer track. But how about the flash memory? So flash memory is a solid state memory. It's not mechanical drive. So we can think that, oh, if the flash memory composition is very similar. So we learned that the composition of the flash memory is similar to that of the RAM. So we may think that, oh, based on the logical block address, the location of the flash memory channel, way, die, plane can be determined. That's it. So how can we handle the performance of the flash memory inside of the storage system? But it's not true. So actually, like the DRAM, like virtual memory, so I already explained in the previous class, the logical block address of the so requested by the operating system is converted to the physical page address PPA inside of the SSD. And then based on this physical page address, we can generate the number of channel number and also the way number, die number, and plane number in the flash packages. So based on this translation scheme, the performance of SSD can vary also. Because based on this scheme, the request can be parallelized or requests can be given to the flash memory sequentially, because the flash memory is composed of multiple channels. Also, way pipeline. So, in the way level, multiple flash chips are connected to the same flash memory bus. So that means that the data bus is shared by multiple flash memory. And then the resources, the hardware resource of this memory bus is limited. So let's think about this. This is the shared memory, shared bus, and then shared bus is shared by some multiple devices. So let us assume that this shared bus is shared by 5 devices, and then also the same bus is shared by 2 devices. So we can think that, we can expect that the performance of this topology is higher than the performance of this topology, because the limited bandwidth, so limited hardware resources like bandwidth, data bandwidth is shared by several devices, several I/O devices. So, and then if the number of devices is small, then you can think that, oh, this performance can be higher than this performance. Okay. So, but we can make use of way pipeline for the flash memory. So actually the flash memory commands is flash memory command is composed of multiple phases. It's similar to the DRAM, because so DRAM also first gives some address, like what column address, row address, then also receive the data from the DRAM. And this is performed by in pipelining manner, and it's the same to the flash memory. But the flash memory's command is more complex than the command of the DRAM. So flash memory is composed of many phases, and then we can pipeline these multiple phases of the multiple flash memory commands. So this technique is called the way pipelining. So if we make use of this way pipelining technique, then we can also maximize the performance of the flash memory bus, okay, with the way pipelining. So that means if there are multiple chips, and then these multiple chips are connected to the same flash memory bus, then we can, if the data is interleaved between multiple chips of this same channel, then also we can increase the performance of the SSD. Okay. And then die interleaving. So die is also similar to the bank of the memory. So each die works independently, but multiple die share this flash memory interface. Okay, so that means each die has the structure of the die is very similar to the structure of bank of the memory. So that means If you see the bank of the memory, then you can find that, oh, this is the memory cells, and then also you can find the sense amplifier. So actually, this is the low buffer. So actually, in a bank, the entire row is read from the memory cells, and the entire row is cached in this low buffer because it's a sense amplifier. And then based on the column address, the target column data is read from this low buffer. That is the structure of the bank of the DRAM. Then the die is also similar to the bank of the DRAM. So each die has the data register and then cache register. So also the memory cell of the flash memory is similar to the memory cells of DRAM because it's a solid state memory. So the data is read from the memory cells of the flash memory, and then actually its word line is read from this memory cell, and then this data can be cached in this cache register or data registers. So actually we can make the multiple cache space for each die, and then if data is cached in these registers, and data can be read by the flash interfaces. So multiple die can work independently, like the multiple banks work independently in the DRAM system. So we can also apply the die interleaving, okay? And we can make use of flash level parallelism, okay? And then plane. So with the multiple planes, we can use the wide data bus. So like the multiple chips of the teams, with the multiple plane, we can increase the data bus inside of a flash chip, okay? So the plane sharing was, so we can just use the wide bus with the multiple planes, okay? So these are flash level parallelisms. And then based on the topology of this flash memory, then we can make use of parallelism in flash packages or flash memories, okay? So we learned about the topology of the flash memory. This is a memory. So as I explained, the logical block address requested by operating system is converted into physical page address, and then this based on this physical page address, the channel, way, die, and then plane, and then word is determined, and then the data is accessed by these numbers, okay? And then based on the flash memory topology, and then we can make use of flash level parallelism inside of SSD. Okay. So let's see the inside of the SSD. So this slide shows the architecture of SSD firmware. So in this slide, you can find, oh, this is the host CPU. So it's actually CPU. And then what is host CPU runs the user applications and operating systems. And then the host CPU is connected to the SSD via storage interfaces. So we frequently use SATA or NVMe as storage interfaces. But recently, we use the NVMe because the performance of PCIe is higher than the performance of SATA interfaces. So we can generate some software driver for this NVMe drivers. So you can generate some data queues like with the software. Okay, we just use the PCI layer. There is a physical interface, and then under this physical data interface, the NVMe protocol runs under this PCI interface, and then this NVMe protocol is a software. Okay, and then inside of the SSD, there is the SSD embedded processors, and then also this is the general purpose processors that can run SSD firmwares, and then also SSD has the some hardware part, it's a custom hardware part. So SSD need to access the flash memory, also the DRAM. So that means SSD requires the flash controllers and then DRAM controllers here. And then these flash controllers and then DRAM controllers are connected to SSD processors via internal interconnection of SSD SoC. Okay. So in this figure, you can find that NVMe host driver. So NVMe host driver communicates with the SSD processor, actually the firmware of the SSD. And then you can find that there are two queues, this submission queue and completion queues. So the queue is some software data structure that reside in host memory. So NVMe host driver create this submission queue and then completion queue inside of the host memory, and then generate the command, the NVMe commands to the SSD. Then this is the structure of the SSD firmware. SSD firmware is composed of I/O controller, that is the interface between SSD interface, NVMe interfaces, and then also in the I/O controller, the NVMe commands are encoded. Okay, and then this is the flash translation layer called FTL. So this is the unique feature of the SSD because SSD handles NAND flash memory, and then also we learned about the unique features of NAND flash memory. And then in order to handle these unique features of the NAND flash memory, SSD has some unique flash management software. It is called the flash translation layer, and then called the FTL. So this flash translation layer is required for managing flash memory. So based on some applied schemes inside of the flash translation layer, the performance of SSD can vary. Okay, so we can work for this flash translation layer to increase the performance of the storage system. This is very it's a very popular research area in the SSD, the flash translation layer. Also, in this flash translation layer, the commands to the NAND flash memory is generated. So based on the physical page address. So I said the SSD is also a block-based storage system. So SSD receives the logical block address from the host system, and then this logical block address is translated into physical page address in the flash translation layer, and then commands to the flash controller commands to the flash memory is generated from this flash translation layer, and then also receive the data from the flash or the buffer of the SSD RAM, and then provide the data to the host system. So this is the SSD firmware architecture. Okay. So let's see how the page data is read from the read from the flash memory. Okay. So in the previous class, I explained that page is the granularity, access granularity for read command for SSD. And then page is about the 4 kilobyte or 16 kilobyte size. So size of the page can be 4 kilobyte to 16 kilobyte. And then when the read command is given to the SSD, the data is read from the flash memory with, page granularity. Okay. So in the host system, the read command is given to the SSD based on the logical block address. So the size of the logical block address can vary by file systems of the operating system. So usually we can use the 4 kilobyte of block size, so unique block in the file systems. Then if a logical block address is given, and this logical block address is translated into physical page address. And then based on this physical page address, like this 1 and 2, the read command is generated from the FTL. And then read commands are given to the flash memory and then page data. So page data is read from page data is fetched from the flash memory, and then this page data is cached in the SSD DRAM. Okay, and then the page data is transferred to the DRAM of the SSD system, and then based with the DMA, direct memory access, with the DMA protocol, the data is transferred to the memory space in host system, the main memory. And then its data is transferred to the host memory, the interrupt is raised, then the host system can receive the data from SSD. Okay, so this is the main feature of the SSD. Logical block address to physical page address. Then how this flash translation is performed inside of the FTL. So why do we need this address translation? It's because of because of the features of NAND flash memory. So I also summarized the features of the NAND flash memory here. So read or write is performed by a page. So it's a page, page granularity from 4 kilobyte to 16 kilobyte. So this is the feature of the SSD hardware. So based on the flash memory topology, the size of a single page is determined. So this is the hardware feature. So actually the operating system does not know about the internal hardware of this SSD. So we may get some information from the storage system, because some storage system can provide some hardware specification via the administrative commands like SMART technology of the hard disk drive. So similar technology can be applied to the SSD. So the operating system may know the size of a single page, but usually this is the unique feature of the SSD. So the size of a page is not revealed to the operating system. Okay. Also, another feature, another critical feature of the flash memory is in-place write is not possible. The write is only possible for empty pages. So if the page has a valid data, then this data cannot be directly updated. In a hard disk drive, this in-place write is possible. So data is overwritten to a target sector directly. But in a flash memory, this is not possible. So in order to write the new data to an occupied page, we first erase the target page. Then after this erase process, the new data can be written to the target page. And then erase process must be applied at block granularity. Okay, this is the main feature of the flash memory. So let's start from the write of new data, write of a new page. So this is the write request from operating system. So that means that write data to logical block address 0. Okay. So this is the write command from operating system, and then this command is given to the SSD firmware, and then SSD firmware checks the FTL table. So this address translation table exists inside of FTL, flash translation layer, and then usually it's similar to the address translation table of a virtual memory. So if this request is given to the FTL, then FTL SSD check the FTL table. And this table is usually composed of valid bit and then logical block address and translated physical page address. Okay. So in the virtual memory, virtual memory is receive the virtual address, and this virtual address is translated into the physical address. It's the same. Its mechanism is very similar. So the write to the logical block address 0 is given, and then check the FTL table, and then check the corresponding entry of this logical block address 0. Good, but it's invalid. So if the table is invalid, the table entry is invalid, that means the target page is currently empty because no data is written to the target logical block address. Target logical block address is empty. Okay. So this is the operating system, the view of the operating system. Operating system thinks, oh, this is the storage. Storage is composed of many blocks. Then the operating system can access the data inside of a block based on using the logical block address. Okay. So with this logical block address number 0, access the FTL table, or FTL table is invalid. So that means that the target logical block is empty. Oh, this is empty. Okay. And this data should be written to the flash memory, but just remember that implicit write is not possible. So the write of a page should be performed to the empty pages. So that means that a flash translation layer need to find the empty pages is for new write. Okay. So for this logical block address, there is no existing data, and then so SSD finds an empty page from the flash, then the flash memory. So we can find the, oh, this page is empty. So because this is empty, the empty bit is assigned to the this target flash memory pages. So this PPA 0 is assigned to the logical block address 0. Okay, this is the write process. So for the write process, SSD finds the empty page for new write. So and then this this page is mapped to the logical block address. Okay. And then let's see how overwrite is performed. So I said the implicit write is not supported. So we cannot overwrite to the same page because this PPA 0 is mapped to this logical block address 0, and then also the same write command, like write to logical block address, is given to the SSD. So SSD check the valid bit of the FTL table, or check the valid bit, but SSD knows that this logical block address is already occupied. So this is block address. So logical block address is already written by the previous commands occupied. And then this logical block address is mapped to the physical page address 0 here. Then how can we write the updated data to the logical block address? So in this case, it's not possible to update the data to this physical page address 0. Then in order to overwrite the data to this physical page address, the entire block, so it's a group of pages, should be erased. It's not efficient because the erase is very slow. So instead of erase and write again, SSD finds another empty page from the flash memory, and then write this updated data to the new empty page, like PPA4. So here in this scenario, the SSD finds that, oh, PPA4 is empty. So this is empty. So updated data is written to the PPA4, and then new physical page address is mapped to the logical block address 0. Okay, so that means that FTL table entry for logical block address 0 is updated to the new physical page address. Okay. Then what about this old page? Actually, this is the valid state, as you can see. So that means that the data is written to the physical page address 0. And then updated data is written to the physical page 4. So this is the actually old data. and then invalid data. So I said the erase is very slow, and then erase should be performed at a block granularity. So this page cannot be erased immediately. It's a kind of lazy erase. So SSD just check change the status of this page as invalid. So invalid means that the data is already written to this page, but this data inside of this page is an old data, so invalid data. So valid data is stored in the new empty page. So this is the invalid data. So actually, SSD, the old data exists in some old page space. Even though we write the new data to the SSD, this old data still exists inside of NAND flash memory. And then this updated data is written to the empty page. Okay. So if this old data is not erased, so we can find some history of the target page, because if this old data is not erased, this old data exists in the NAND flash memory. Okay. So that's why we if we want to sell our SSD to some other people, then we need to totally erase the entire flash memory in order to remove some private data inside of the SSD actually. Okay. So, and how about the read? So read is actually simple, because this logical block address is mapped to the physical page address 4. Because in this write process, the LBA0 is connected to the physical page address 4 here. So the read command is given to the SSD, then also check the FTL table. Oh, this entry is valid. So that means that this logical block address has a valid data inside of the NAND flash memory. So, and then this LBA0 is mapped to the physical page address 4, and command is given to the NAND flash memory, and then read the data inside of physical page address 4. And sorry. Sorry. And then let's talk about the garbage collection. So because of the write process, this write process of the SSD, the write process may generate many invalid pages. And then if the number of invalid pages increase in the SSD, then the actual storage space in the SSD will decrease, because SSD has many invalid pages. That means that the empty page number of empty pages will decrease. So actual space in the SSD also decrease. So that's the problem. So FTL also support the garbage collection. So garbage collection means that if there are many invalid pages inside of a block, then just erase the entire block. But if we just wait until the all pages in a block becomes invalid, then it will take very long time. And then it will also it may also influence the storage space of the SSD, because let us assume that there are many blocks, and then only one valid page exists in each block. So if we cannot erase this block, then the SSD space is wasted by many invalid pages. So FTA also performs the garbage collection. The garbage with this garbage collection process. So if the number of invalidated pages is large, then just copy this valid pages to the empty page, and then make this valid page into invalid page, and then erase the entire block, entire pages in a block, in a target block. That is the garbage collection process inside of SSD. So with this garbage collection requires the copy of the valid page to the different blocks, and then also it requires the read and write process. And then with the garbage collection, the entire block should be erased. So it requires the erase process. So garbage collection requires the copy, the read and write and erase. So garbage collection may also occupies some hardware resource of the SSD processor. Also, when the garbage collection is performed, the SSD processor is busy, and then so performance of the SSD can be degraded because of the garbage collection. So in order to support the in order to maintain the performance of the SSD, we also need to create some smart algorithm for the garbage collection. Okay. So this is the summary. So SSD architecture is composed of a host interface and then firmware with the FTL and then flash memory packages. And then we can use the host interface. We can use NVMe or SATA interface as the host interfaces. But in this course, we will learn about the NVMe. We will focus on the NVMe because the SATA is the somewhat old storage interface, and then the performance of SATA is lower than the NVMe. And then firmware. So SSD runs a system software called firmware, and then firmware performs the instruction decoding. So it decodes the command from NVMe protocol, and then SSD firmware also has the flash translation layer called FTL. So FTL manages the flash memories, and then FTL performs the address mapping, the logical block address, the physical page address, and the garbage collection, so where labeling. So I did not explain about the where labeling because we will learn about the where labeling later. So actually, based on the several algorithms for address mapping or garbage collection, the performance of SSD can vary. So this is active research topics in the SSD. The flash memory. Also, we learned that flash memory has a hierarchical topology, and then based on this topology, we can exploit the flash level parallelism like theorem. Okay. So these are what you learned for this SSD architecture. So we briefly learned it briefly. So in the we learn also detailed algorithm of address mapping or garbage collection or some flash level parallelism later. So we briefly learn about the SSD architecture. Okay. Okay. Let's take a break for 10 minutes, and then I will be back at 11:55. Okay. 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 Let's move on to another topic of today's class. Okay. Before starting the next topic, so this is the very next day of the long weekends. Usually, students are not easy to uh, hear, pay attention to the classes after long weekends. So, so I can hear some noises are recorded to from my mic because so my office is near the normal street, so I believe you can hear some noises from my mic. Okay, let's move on to the next topic of this class. So in the previous classes, we learned about the brief structure of the storage devices like hard disk drives and solid state drives. And then in this time, we will learn about the file systems. So actually, why we create files and then we store files on the storage devices. And then these files are maintained even though the power of computer system is off. So actually we see files, not data in the storage devices. So we just manage these files and then also our applications and operating systems manage the files and access files and update files on the storage devices. So in this time, we will discuss how files are generated and then managed and stored in the storage devices. So let's start. So if you read the operating system, the textbook of the operating system, like 3 steps of operating systems, then you can find that there are 3 representative abstractions by operating systems. So these abstractions are just like illusions because so under the so inside of the system or hardware is very complex, but we think that this hardware is very simple. And then also we just understand what we need to understand between under for the under layer. That means the lower layer. Okay, so it's very similar to the illusions. So actually, uh, operating systems use many abstractions, and then because of these abstractions, we can understand the only required things regarding the lower layers. That means the hardware. So operating system use the processes or process. And then this is a virtualization of CPU. The CPU is the real hardware and the instructions are executed inside of a CPU. That means the processor, the hardware processor. But an operating system can create many processes and then each process run on this processor hardware. But we do not consider about the number of CPUs or number of processes. Also, the software does not consider about the performance of processors because operating system just think that one CPU or one processor can handle one process. This is the software. And then each process is assigned to the processors independently. So what is the illusion? Each process is handled by a single processor or multiple processors. So it's like this. This is software. So actually operating system. Operating system may generate hundreds of processes. And then actually these processes share the several processors. So it's a hardware, the CPUs. But we have only tens of CPUs, like in the server systems. Also, we may have 8 cores or 8 CPUs inside of our systems. But these many processes can run concurrently using several hardware processors. So that is an illusion. So many processes share a single CPU. That means a single core, and then but we can switch multiple processes assigned to a single CPU. So that's how operating system use the virtualization of CPU, that is a process and address space. So I repeatedly explain about the virtual memory, that is the address space provided by operating system. That is another illusion provided by operating system. So operating system use the virtual memory space. So that means this large memory space is assigned to each process. So each process independently can handle this large virtual memory space. So this is another illusion provided by operating system. And then another illusion is the file system. These file systems are a file system is a virtualization of persistent storage. So I already explained that storage is just a block-based memory. So that means that a storage device is composed of many blocks, and then actually the data is stored in these blocks, and then the data inside of a block is pointed by block address. That is the logical block address. So that is the block-based memory. So just the block-based memory. But we do not directly access storage devices like main memory. So how can we access the main memory? So this is the main memory. In order to access the data inside of the main memory, we need to access this target data using address. It's actually this is the pointer of a variable. That is the address. So actually this is the virtual address. But how about the storage system? We just create a file, and then we store this created file inside on the storage devices, and then we can update the contents of a file. So this is a virtualization of persistent storage. And we know that this file will not be removed even though we turn off the computer systems. This is the persistent storage. So this is another illusion provided by operating system, because even though the files or directories are stored in this block-based memory, we do not see that this block-based memory. We just handle the files or directories. So what does that mean? The file system is entirely software. It's not hardware, because hardware is just a storage system. So it's a block-based memory. And then based on this block-based memory, the software is organized. So that means that the data structure file system is just the software. So, and then file system just generate data for files and directories. And then this data is organized. That means that the file system is similar to data structure stored in the block-based memory. And then based on this data structure, operating systems manage files and directories. So I said this is the data structure. So this is very similar concept of the database. So database also handles the many data on the storage, and then in order to access manage these data, the database systems use various techniques such as index structures or index management or some data query processing like data accesses. So like these data structures, the file system also generate the data structure for file data and then manage the files and directories on the storage devices. So this is like a virtual memory. So with the virtual memory, so under the virtual memory space, there is the physical main memory and storage, the swap space. So actually, the software just sees this virtual memory space. The software thinks that every data inside of virtual memory is the same. So what does that mean? In the real world, that is the physical world, the data can be stored in the main memory. It's a very fast DRAM. Also, some data can be stored in the disk. It's very, very slow, but it's a large space. But software does not know which data is stored in the main memory or which data is stored in the disk, the hard storage devices. Operating system knows, but software, that means user application or user processes, do not know which data is stored in the main memory or which data is stored in the disk. Software just access the data using the virtual address. It's a pointer of a variable. And then the data movement or some response to this data request is managed by operating system. So this is the software's view to the memory. It's very constant, large data space, data memory accessed by virtual address. That is the software's view. But in reality, in the real world, this memory is composed of page table or also TLB is the hardware. It's a main memory, storage systems. It's very complex, but with the in the software's view, is very simple system. It's the same to the file system. So actually, this is the storage system. And then it's a storage system which is composed of many blocks. And then this block is accessed by logical block address. And that's it. That is the simple view of our storage system. That's it. But under this block-based memory, block-based persistent memory, operating system manage the files and directories. And then actually the application, the apps, just handle access the these files and directories. So what is the file? So file is just a bunch of data. That's it. Right. File includes our data, the user data. For example, a database file has some data sets or some data for each keys inside of this database file. And our word processor file also includes the document contents of the document and then some options of this application. So this is a bunch of data, and then group of data is just stored in the storage device. The blocks, this data is stored in the multiple blocks of the storage system. That's it. But application, so for the application, it's not easy to access these data stored in the storage devices. So in order to access the target data, the application needs to know the location of the target data. That means the logical block address to the data of data. But instead of access the data using the logical block address, application just access the file. And then this file, that means that this file has the location information, that is the logical block address to the target data. So accessed by applications. And many other information is also handled by this file. So that's why the file system also has the metadata, that is the information of the file of a certain file. Also, the file, it has the real user data. So user data is also inside of a file. So that's why file system is a data structure for the block data on the storage system. Okay. So this is another illusion for the persistent memory. So I said the file system is also a software, and then this is the a virtualization of the persistent memory. So that means that the all information about the file system should be stored in the storage system, because this is a persistent memory. The content of the persistent memory is not removed or erased, even though the system crashes or power loss happen. So that means this is the file system. And then this file system is the data structure for the user data on storage system. And then this is data structure on the persistent memory. So that means if a user or user application updates the data on this file system, or that means the data on the storage system, then this data or file system should be maintained for a long time. So sometimes the data can be corrupted by the crashes on the storage system, but so we do not guarantee the 100% of the safety on the data on the storage system, but the persistent memory guarantees the maintenance of the data for a long time. Okay. So the information of the all file systems are stored in the store devices. So it's a block-based memory. The file system, the file system is that it's the data structure that handles the files and directories. Then this information is also stored in the storage system. So also we know that the data of the operating systems are also stored in the storage system. So that means this operating system is the data of the operating system is transferred to the main memory, and the operating system also manages this file system of the storage devices. And then operating system reads the file systems, and operating system regenerate the original state based on the stored data in the storage devices, because this is the persistent memory. Okay, and then also we can regenerate the some original state by reading data inside of a file. So it's also kind of concept of the persistent memory. Okay, the file system means the file systems implement an abstraction. So that means the file is the bunch of data stored in the secondary storage. That's secondary memory. And then file systems also organize files logically. So we frequently use the concept of directories. So directories are just a directory is just a group of files. It's a group, actually a set of files. So if we handle the files inside of the directory, then we can efficiently handle the many files. So that is required for file organizations. And then based on this file data, the operating system permits the data sharing between multiple processes, and then multiple people, and also the multiple machines. That means the multiple systems connected via networks. So for example, the database systems. So database in the database system received many queries from the many users, and then database system respond to these multiple queries from multiple users. So also operating system managed this data sharing of the file system. Also security. File systems provides some permissions or user privileges for each file or each directory. Okay, file. What is file? So we frequently use our user data. So we frequently store our data as a file. So what is a file? So we can think that, oh, so file is a very special data, because a file has its own extensions like txt, jpg, or .c, or it's a source file, .obj, object file, or .exe, execution files. It's a binary file. So we can think that a file is a very special form of data, but actually, file is a sequence of bytes. So that is just a large, it's a bunch of data. It's actually a sequence of byte data stored on the storage systems. Okay. Yeah. It is also true that the file can have metadata, that is some special information for a specific file, like permissions, access time, or some file types. So this metadata can be included in the file. So that is just all data. Okay, so some normal data. So it's similar to data stored in the main memory. Okay, but this data is managed by operating system as a file system. Okay, as a file. Okay. And then as I explained, the file may have different types like extensions based on the extensions, but these extensions are used for an user convenience. So that means the computer systems, actually the computer hardware cannot distinguish different extensions or different file types. So actually we can set the JPG extension for any text files, I mean, that's fine. This extension is also kind of name convention. So, and we can use those different extensions for, actually it's the same, very similar to different title. Okay, these extensions are only used for some convenience. Okay. So it's just the name, but the file is just the data. Okay. So in order to access the data inside of a file, we can use some many access methods, such as the sequential access or direct access. So actually, we frequently use these two types of accesses. So sequential access means that the data blocks of the data blocks inside of a file is accessed sequentially. And then direct access is the random access. So that means that this is the file, and then file has its metadata information, and then file has its own data blocks. And then we can sequentially access these multiple blocks inside of a file. That is the sequential access. So we can access these blocks from top to bottom sequentially. And then random access means that we can access a specific target block inside of a file. That is similar to the random access to the main memory or random access to the storage devices. Okay, with the logical block address or some address for data. So direct access. Some specific access method is the record access or indexed access. So file systems can be accessed with indexes. So we frequently use this index structure in database systems. So with the indexed access, the file system can have indexes, and then based on this index, then files. So we can read some specific data inside of a file based on the indexes. And then also record access means that the file is accessed by some record number, and then so sequentially or randomly by record number. Okay. And directories. So if the directory is the group of files that, and then we store these files under a directory. So this is just a list of files. Okay. So I said that the storage device is the block-based memory. So actually, each file occupies the multiple blocks. And then in the storage view, the files are just data. So each independent file just occupies the block spaces inside of a storage device, and that's it. But if the whole file level is flat, then if there are many files inside of storage devices, then it's not easy to organize the file by some normal people. So directory means just the group of files, and that's it. The directory is just provides the list of files grouped inside of a directory. Okay. So directory is just a data structure. So for example, we can store some files like foo, bar, F1, F2 inside of a directory A. Also, we can store another files like F3, F4, F5 inside of directory B. Well, if we organize files like this, we can easily find the target files. If we remember which file exists in which directories. Okay. But in the computer system, just directory A means that A has the file foo. This file is located in logical block address 1, 2, 3, and then so as the bar. This is LBA from 3 to 5, and the F1, F2 is a LBA 1000, LBA 1001, and that's it. The directory is just a list of files, and then actually files have of single level, that means a flat level. Okay, but based on the this directory structure, software or user can approach to the target file. Okay, and then that's true for us actually. So we store our data inside of a directory, and then in order to find a certain file, then we just navigate the multiple directories, and then we just use the ls command on the Linux, and then you just see the list of files inside of the directory, and then find some target file in the directory. Okay, that's how software works, and then that's how our normal people work for these file systems. Okay. So the structure of the directory looks like this. So this is the root directory of the Unix system. And then under the root, there can be multiple files or multiple directories. So this figure shows the two directories like called foo and bar. So I said, directory is the list of files. So that means directory just has the file number. This is the inode, and file name. That's it. That is the entry of directory. And then directory includes the multiple entries if the directory contains multiple files. So that means a directory can have multiple entries. So what is this? This is just a list data structure, list structure. What does that mean? Directories are also just a file, like data. But it's a specific file that contains the list of other files. Okay. And then under the directory, you can find the specific file called the bar.txt. So this is the file name. But operating system assigns the specific file number to each files, each file. So for example, this number is called the inode number in the Unix systems. So actually, operating systems assigns some specific inode number for each file, like 1000. So it's the inode number for bar.txt. Directory also has its own inode number. So I said that directory is also file. Okay, so like 999. This is the inode number of foo, and then this is the inode number of bar.txt on the foo directory. So what does that mean? This foo directory has the inode number of the bar.txt, like 1000 here, and the file name is the bar.txt. That's it. So that is the content of the directory, and then inside of the directory, there is a file, but file is the independent data structure. And then file includes the metadata, that includes also inode number, that is the file number, and then several information like permissions, and then a file size, some access times, access steps. So kind of metadata also include the pointer to the user data, like LBAs, logical block addresses, like logical block address 100, 1000, 1001, 1002, 1003. So there are four blocks are occupied by this file. So it's a kind example of the LBAs. This information is grouped and stored in the inode data in the file system. Okay. So in this figure, there is another directory bar, and the inside of this directory, there is the same number, same name of the directory bar. It's possible, right? You can set the directory name, the same directory names under this parent directory, like a bar and bar, but inode number for this directory is different. It's obvious actually. So 998 is the inode number. The inode number for bar can be 997. So different numbers are assigned to different files and different directories. And under the bar, there is another directory named foo. So this inode number is different. So each directory or each file has its own inode number, it's a specific number. And then based on this inode number, then files and directories are managed by operating system. Okay. So as I explained, the directory is a list of entries like name and location. So name is just name determined by applications or users, and location is the inode number. Okay. And then this list is usually unordered. So that means the list can be, there is no order in the directory. So if the new file is included in the directory, then new entry is just added. And then if the if a file is removed from a directory, then this entry is just removed from a directory data. Okay, so the order is the unordered list. So the directory is just it's just like other files. Like that means it's a data structure. It's just a data structure. So in a application or users view, so we think that, oh, this is the root directory, and under the root directory there can be many files on the many directories, and then there are many trees of the directory under this storage devices. But it's just an abstraction. But these all structures are stored in the storage devices as software. Okay. So let's see how the path of the file is translated. So let us assume that an application tried to open the file 3 under the directory 2 and 1 on the root directory. So this is the root directory. This means the root directory. So how can you approach this target file? So the first, an application opens directory root. The location of root directory is some specific, is stored in a specific location of the storage device, like a first block of the storage. It's some specific, it's a predefined location, because this is I said the file systems are software. This entire data structure should be stored in the storage devices. If not, if this information is stored in the DRAM, then if we turn off our computer system, then this information will be removed and erased. We cannot recover this information. So this information is stored in the storage devices, and then the location of the root directory is stored in a specific, that means the predefined location of the storage devices. Here, so it's the first block, or first logical block, LBA, of the storage devices. I said that is the logical block because the physical location can be different. Okay, so open the root directory, and then this information, this data, that means the list of the list entries inside of this root directory is transferred to the main memory. Then operators, this data is decoded, and then also find the location of directory 1. So I said in the directory has the list of name, is some text name, and then location, that is the inode number of another directory, another folder, another file, or another directory. So just search the name 1, and then if we find the name 1 from a directory, so root directory, then we can figure out the location, that is the inode number of this directory. Okay, then we can access this directory. So if we just inode number, that is location, then we can access the logical block address from the metadata of this file. Actually, this is a directory, but I said that the directory is actually the same to the file. So we can access the logical block address, And then if we access the logical block address, that means the data of directory 1, you can access the list of the directory 2, like name and then location of directory 2. And then if we access the data of this directory 2, then we can also get the location of the file 3 here. This is the inode number. Now if we get the inode number, then we can access the file, and then we can open the file 3. That's how we approach to the target file on the storage systems. Okay. So this is the actually data structure. And then in order to access the target data, we need to traverse the defined data structure. That is the file system. And then as I explained, in order to access some leaf node, that is the last node of this tree-like structure. In order to access this leaf node, we need to start from the root of this data structure, and then we need to find the branches and on the low-level nodes based on the list structure. So in order to access leaf, we need to access many blocks on the storage devices. That means storage devices are accessed many times to approach the target file of the application. And that's why the structure of the file system also influences the performance of storage devices. Okay. So, this is some metadata information, also provides the permissions or some allowed users for these files. So if you are familiar with the Linux file systems, you can find that the permissions for files like read, write, and execution, RWX permissions for each file. Also, these permissions are applied to a certain users, work group, or root as administrators. Okay. Also, the permissions are recorded in the metadata field of the file, and then based on these permissions, this file can be accessed by a certain users, or this file is hidden from a certain user groups. Okay. So the protections are applied to files based on the metadata. And then I think I need to explain about the file system layout in the next class, because it's also it's a big chunk of the topic. Okay. Okay. So I will stop here. So in today's class, we briefly learned about the architecture of solid-state drives. So we briefly covers some file systems. So what are file systems, and then why file systems are organized, and then how the file system provides the simple abstractions to software or users. Okay, so just to remember that to the operating system, the storage devices are just a block-based memory, and that's it. But under this block-based memory, the operating systems just provide additional layer, abstraction layer called file system, and that is the software. And then based on the software, applications or users can access stored persistent data called files. Okay. Okay. Thank you for your attention. And do you have any questions? Okay. So actually, I don't. Actually, NTFS is designed by Microsoft, and then NTFS is some commercial file system. Actually, it's a commercial operating system, so it's not revealed to the public. So usually in this course, in this course and in this class, we will learn about the popular Unix-like file systems because this open source operating system. So, but we like expect. So maybe the file system, another file system can be more efficient compared to this Unix-like file system. So, for example, you mentioned the SQL-based metadata. So why database systems use SQL-like? So that's the index structures or some key value structures, because that is more efficient. So some database systems use each own specific file systems. So I think I said the file systems are just illusions. So that is just show the structure of the structured data. So that is a data structure for some bunch of user data, like actually the group of blocks stored on the storage system. So some database systems does not use file systems. It directly accesses the stored logical block address of the target data by managing index structures. That can be a possible solution for more powerful database systems. That means the more efficient database systems. Okay, so we can develop the more efficient file systems like EXFAT, as you mentioned. Also, we can develop the more efficient file systems for different storage devices, such as SSD or flash memory-based storage devices. So, have you ever heard about the F2FS? So that is the flash memory-based file systems. So actually, the many performance issues can be raised because the operating system just handles the storage system like a block-based memory. But inside of this storage system, the mechanism is very complex, like hard disk drive or SSD. So we can apply some more efficient specific file systems based on the unique feature of the storage devices. That can be possible. But in this class, actually the Unix-like file system is the most popular file system actually in academia. So it's not easy to access the commercial file system like NTFS. So in this class we will learn about the Unix-like file system. So okay. Okay. Thank you for your attention, and then see you in the next class. Okay, bye.